I wanted to have a look at an example of a composite function and deciding whether or not the composite function exists. So this one should hopefully be a pretty straightforward example. So the question says, consider the functions f of x equals 3x plus 2 and g of x equals x squared. So the question is saying determine if f of g of x exists and g of f of x exists. Okay. A composite function is basically a function where you take the second function, or the inner function, let's call it, and put it inside the outer function. So if we look at f of g of x is the inner function and f of x is the outer function. So in some ways, what we're doing is we're taking the outputs of g of x. Outputs correspond to our range values. And then we're substituting those, whatever the output of g of x is, into f of x. And then we're graphing the result, or we're finding out what the result is from there. So this is the rule we need to be aware of in terms of the existence of a composite function. So f of g of x exists if the range of g of x is a subset of the domain of f of x. And that should make a bit of sense, right? If we just think about it in terms of the machine analogy, g of x is some machine. I'm going to take some x value, put it into g of x, and then that's going to give me some output value for g of x. That output value for g of x then becomes the input value for f of x. So you can see why the range of g of x, the outputs of g of x, have to be a subset, have to be within the domain of f of x, because there's only certain things you can put into f of x based on whatever its domain is, and the outputs of g of x must satisfy those, because you can't put something into the machine that won't allow it to go in. Okay, so that's one condition. The other condition is if we do it the other way around. So g of f of x exists if the range of f of x is a subset of the domain of g of x. That's just the other way around, right? F of x is now the inner function. So the outputs, or the range of f of x, must be inside the domain of g of x. So let's do this example to see if we can make some sense of it. So the first thing we're going to do is we're going to draw f of x. So f of x is 3x plus 2. That's a line that looks something like that. And what we can say is the domain here is all real values. Remember, domain's thinking left to right, all possible x values. This can go from negative infinity to positive infinity. And the range you can also see is from negative infinity down here to positive infinity up here. Okay, and then we can do g of x as well. So g of x is going to be, it's going to have a domain of all real values. So you can go from negative infinity over here to positive infinity over here. The x values can take on any x values. That's all real values. Call that capital R. Okay, the range I encourage you to think about, the range is not quite from negative infinity in this case. The range actually starts at 0, and then it's all positive real numbers. As you can see, the smallest value of g of x is here at the origin, and then we only go up. So the way we write that using what's called set notation is I'm going to say all real positive numbers in union with 0, so including 0. Okay, so what we have here is this nice table can help us determine if f of x and if f of g of x and g of f of x exists. So let me just get rid of these now. And now let's put in so what we have here is the composite functions. We've got f of g of x, which is 3x squared plus 2. And the way we get that is we take the function f of x, and wherever we see an x, we put g of x, which is x squared. So substituting that in, we're going to get 3x squared plus 2, which is the graph that's shown in blue. And then g of f of x is we're taking the function g of x, and wherever there's an x, we're putting f of x. So it's going to be open bracket 3x plus 2, close bracket, all squared. So that's in orange, and then in blue is f of g of x. Now, clearly, just the fact that I've drawn them shows that they're defined. But let's think about why they're defined. Let's look at f of g of x, so the blue function. So the range of g of x is a subset of the domain of f of x. So let's have a look. The range of g of x is all real positive numbers, including 0, is a subset of the domain of f of x. Well, let's see if that checks out. Does this thing here fit inside that? And hopefully you can see that it does. All real numbers is a larger set than all real positive numbers, including 0. So this thing, the range of g of x, fits entirely within the domain of f of x. So we're all good, and the composite function exists, and that's what it looks like. It's that blue line. Okay, and then let's do the other one. G of f of x exists if the range of f of x, okay, the range of f of x is all real numbers, is a subset of the domain of g of x. Well, g of x is also all real numbers. Now the question is, are they subsets of one another if they're equivalent to one another? And the answer is yes. So as long as, yeah, they're equivalent to each other, or one fits inside the other, we call it a subset. So that obviously turns out to be that orange line. And then basically we know their existence now. We know that both f of g of x and g of f of x exist. Now later on, you'll do harder problems where you need to restrict the domain such that the output values of the inner function satisfy the domain restrictions of the outer function. Now that was a mouthful, but you'll do examples later on where you need to make restrictions such that the composite function f of x, f of g of x, or g of f of x exists. Hopefully that clarifies how to work with composite functions. Drawing up a table like this can be very helpful.